So here's the overview. We're right now doing the summary of resources, and this whole presentation is basically a whole bunch of links that you may find useful afterward. And I've posted these slides in PDF form to the Slack channel if you want to download them. They'll also be available in the JWebbinar 25 materials. Then there's going to be a scripted search for potential duplications, which I'll give you right after this one. And then there'll be a somewhat more advanced notebook that Thomas will go over, talking about scripted MAST queries, so looking for time series spectra of exoplanets. So that could be fun. Then there's this new JWST search tool in MAST, which is a demo. This tool has not yet been released, but we expect it to be released in the next month or thereabouts, few weeks. So you can give it a try and see what it's like. And then, like I said, if there's time, we'll talk about DOIs. I'll just emphasize that if you have questions, please put them in the Slack channel, because there's a fair chance that Thomas can answer the questions, or during the breaks we'll have between each of these little sessions here, we'll have a chance to go over anything that might be you might be wondering about. So here we go with the links. We have links to MAST notebooks. These particular notebooks we're going to cover today. The API for AstroQuery. There's the JWST archives manual you may find helpful. JDocs, which is the instrument descriptions, also includes data quality and calibration information. That's your primary resource for JWST information. And of course, there's user support. You can drop us an email, archive@sjsci.edu, or use the ServiceNow web address, both for the MAST archive or for JWST questions, if that's more appropriate for you. For Cycle 3 resources, there's a few additional things. There's the call for proposals. I'm sure you've seen that, but it has a lot of information in it, including some policy that applies to what we're going to talk about here, which is duplicate observation policy and checking for duplications. And again, user support for JWST also will provide information for you about duplications. I'll just do a digression here to talk. I'll give you a few notes about other kinds of searches that can be done. MAST also features graphical interfaces for various searches, and these in the table here are the primary web-based tools for JWST. Many of them relate to what we call the portal, which is our multi-mission search application. But there's this new MAST JWST search form, which will be rolling out soon. What we're going to do is look at the test version. That's why the URL has that blue text in it. You'll be able to look at that. I'll just caution, and I'll have to do it again, caution you that new search tool is not appropriate for doing Cycle 3 duplication checking. There's a few reasons for that. One is that it's not feature complete. This is just the initial rollout. And the other is, most importantly, it does not yet have access to JWST planned observations. And that's very important. A lot of Cycle 2 programs have yet to be executed. And finally, there's the DOI portal, which we'll get to if there is time. You can take a look at the portal user guide for details of how to use the MAST portal search. I just want to emphasize a few technical terms, and please keep them in mind as we go through this. I think most of you may know what a program ID is. It's similar to a proposal ID. That's what MAST calls it, and that's what HST calls it. Just a numerical identifier of the science programs. Observations is a big one. There's the kind of observation where it's just one of a set of observations you might conduct in an APT program for the observatory. But MAST uses observation in a special technical sense. Big O observations are really placeholders, so you'll see results that are placeholders for all levels of data products that were generated for a given exposure of a target. Also ancillary information and so on. So keep that in mind. There's a distinction of observations, which are just collections, and we'll show you how to get to what the contents of the collections as we go through the various demos here. Then there are levels or stages of data processing. Data come down from the spacecraft in a fairly raw form, and the lowest level you can get to, we call level 1B. And then they're processed by the processing and science calibration pipeline, and ultimately get the physical units, which is level 2B, and ultimately data products are combined for level 3. So in the big O observations, those collections include all levels of data processing. Finally, I think you probably know about exclusive access data, which basically a lot of programs have an exclusive access period of up to a year, so that the investigating team actually has a chance to publish the data. But then they expire after a year, so data become public. So if you have an interest in including that sort of data, you'll need both a login, which you already have because you're viewing this session, and authorization to access the program. There's a MAST accounts webpage to look at for details. All right, so a few tips and pointers for product searches. Again, this is more obvious in the portal, but it's also true in the API. There's a distinction between searching by object name or coordinates, which gives you back results, which are these big O observations or collections. You can also search by JWST instrument keywords or using the MAST class in AST query. So that allows you access to criteria that are a rich set of metadata that are unavailable with other methods. For instance, you can get the time series or filter for time series data this way, but it only returns the highest level science files, that is files, not observations, which are the collections. And generally, if you're looking for level 1B files, you probably won't find them that way. The observations themselves, each result, may link to hundreds or even thousands, or I've seen tens of thousands of files on the back end. So once you get to these observations and find the products, you're going to want to use filters in the download basket and in the MAST portal, or in the product search within the API. You want to filter on that to select the files you actually care about. It's best if you have a lot of files and you want to retrieve them to use a download script. There's a way to make a bash script which contains a bunch of curl commands to retrieve the files in a more robust way than doing it, say, through a browser or a given active session in a Python session. Again, if you want to access the exclusive access data through the API, you're going to need a MAST token, and there's a link here for you to actually do that. Now, a few notes about identifying duplications, which is the segue into the notebook we're going to cover. So there's a little quote here from the policy, but one of the first steps you're going to want to do in your cycle 3 proposals is to determine whether targets or fields you want to observe will duplicate any planned or executed observations. This could be a time saver, right? Doing it in advance gives you a heads up of whether there might be a duplication issue, and you'll have to prepare either a justification if there is a duplication, or rework your program with alternate targets. So I recommend you do this first. And we have the following approach, which when you think about it, it's probably what you would do anyway. And that is to search for observations that overlap spatially with your target or field. And if you don't find anything, you're done. There's no duplication. If there is a potential duplication, that is overlap in spatial position, then look to determine if the instruments and configurations are similar to what you want to use. And if that's true, then look in more detail and determine if the overlap in passband and spectral coverage is similar, and also the exposure depth is similar. And it may be there are cases where you're going to want to take a look at the detailed observing plan for programs that might have overlapping observations with yours, and we'll get to that during the demo. Here's some tips and pointers on that. Like I said, do not use the new JWST search tool for cycle 3. It's just not ready for that. Avoid searching by the target name. The target names sometimes don't resolve to the correct coordinates, and I'll show you a good example of that. But search instead by coordinates or coordinate ranges. If you find certain programs like MAST or SAS spectroscopy or time series of exoplanets MAST doesn't have enough information to give you in detail whether there's an exact duplication. You're going to have to go look at the actual program of whoever observed that target before. So that program, actually, there's a prescription. We're looking at the page that actually has the proposal status information. I'll show you that in the notebook that we'll cover. All right, so the notebook starts out with narrative that I kind of gave you in the introductory slides, and it talks about the duplication policy and what that means. Note also that there can be duplications between, say, NIRCam and nearest imaging, or NIRCam and near spectroscopy, because they have similar capabilities. So we're going to talk a lot about using the astroquery.mast package to search MAST. Here's a disclaimer, which is that for planned observations, that is, those that are approved but not yet executed, the complete footprint is not necessary of mosaic or parallel observations is only approximate. That is, while the primary location is reported, the exact orientation won't be known until the observation is scheduled for execution on the spacecraft. And just be aware that if you're close to an overlap, you'll want to take care in deciding whether there might be a duplication. This is particularly true for slit or MAS spectroscopy, right, where the alignment of the slits, if it's a parallel field, that may not be known in advance, for example. You're responsible for evaluating those details and justifying them in your proposals if there might be one. Now, we already talked about the strategy. So if there is a likely duplication of your target, really you can do the following, right? One is to include in your proposal scientific case for duplicating the observation. And there are examples of this which are perfectly acceptable, right? If your target is variable in time, has temporal variation, and you want to observe when the source is in some different state, that's perfectly fine, as long as it's scientifically interesting. So that would be an example. There are other cases like looking at transits of planets, transits of exoplanets around their host stars. And if it's a multi-planet system, then the prior observation may be looking at one planet. Perhaps you want to look at a different one. So the target and everything else would overlap, but the exact timing would not. So or you can alter your intended observations in a way that does not duplicate by using additional capabilities on JWST. Or you could just plain choose a different target. All right, so let's get going here. So this first cell is just setting up some display happy things for the notebook. What we're going to do now is import the packages that we need, and that's mostly AstroPy, various sub-packages of it, and astroquery.mast, the MAST and observations classes, for example, and a little NumPy, just for fun. So I told you that looking at the detailed proposals of programs you might duplicate is a useful thing to do. So this first utility routine that we're going to execute here is just one that provides a recipe to generate a URL, which you can use right here in the notebook to go to a different page. The next is a utility routine. It's just some of the arguments that we're going to be using in our queries need you to provide coordinate ranges, and it's a minimum maximum coordinate range. And so you specify those in a Python list. And so this routine just takes a given position and an extent and returns min and max of RA and DEC. So that's just a handy routine to have. Next, we'll do queries by target position. Here we come back to the source name thing. When you look for potential duplications with fixed targets, searching by target name is probably not reliable, consistent, or even complete. So you may be fooled into thinking you've got no duplication when in fact there might be one. The exception would be for matching object names of well-known solar system bodies. In that case, you can search by name. Obviously, searching by position isn't relevant for a target that moves. So searching by name will work in that case, provided that it's known to MAST. You can use a routine in the MAST class called resolve object to actually give you back the coordinates. So I'll show you this example. Our recommendation is that you look at the coordinates that MAST would give you and make sure that they agree with coordinates you expect. And you can look at Simbad or some other external source if that's what you need to do. So if that's the case, then searching by target name might be okay for you. So the next thing we're going to do is do the query, right? So this is the observations class of AstroQuery, and the method is query criteria. So these arguments are all criteria to limit the search. The one that's probably most important is the obs collection equals JWST. That limits the search to just JWST and not all the other missions that are hosted in MAST. So that'll make the query execute a lot quicker. It's a key in the database. That's what it amounts to. In this case, as I said, we're going to search for by object name, and in fact, 20 arc seconds around that object name. And we're actually going to look for the number of matching observations. And that number is 0, so we're the big winners here. No results, which means that there is no potential for duplications on this particular target, if that's your interest. Now, for a single moving target, again, you pretty much are without great difficulty. Searching by name is probably the easiest thing, but again, we use observation collection as JWST, but here the target name, you notice we're going to search for IO, but I've given a wildcard character, this asterisk. And so that'll search for anything that matches IO and anything else, like, maybe the target was specified in a prior program by IO, offset, or IO, prime target, or whatever they might have said. So this will match all of those. And it turns out there are 29 matching observations. So you need to look at them. We've got a potential duplication. What do we do here? So we're going to take a look at, these are just the columns that I'm going to display here, the out columns. And we're going to show that in Notebook. So we're going to take a look at what was returned. This is a table, an AstroPy table called OBS. And we're going to look at the contents. And we notice that for IO, it's been observed by NearSpec in IFU mode, Nearest in AMI mode, MIRI in IFU mode. In fact, it's pretty well observed. The other thing I'll point out here is that I'm returning or taking a look at the calibration level of the products. And usually it's 2 or 3. When it's -1, that means that the observation is not yet executed. It's a planned observation, so you have to watch out for that as well. But this at least gives you a sense of the state of the observations. So, all right, so we know that all these observations have taken place. What do we do? Well, let's take a look. We're going to look at the titles. Sometimes the title can be illuminating. Here's the proposal IDs, unique proposal IDs, and the titles of each of them. It maybe will give you a sense of what the observer was looking for in the observation. And this next, it also gives you the URLs, right? The proposal URL. Again, we had this helper function which would generate the URL. So if we actually, let's see, run the platform here. So that should, so what this will do, let me pull it up, is take you to a page which is the program status, has a bunch of information about the proposer and all that. Look at the public PDF file, which is what the proposer submitted, and it will tell you in detail about the observations that were executed. So that's a way to find out additional information that maybe is not available in MAST. All right, so that's the basic technique, is to query for observations, look at what you've got, and decide if it's going to conflict with what you have in mind, and then look at the program ID and the actual proposal if you need even more detail. The next thing we're going to do is check for a list of targets. This can all be done with the MAST portal, and that's perfectly fine. And one advantage of the portal is that you can actually also see the footprints of the apertures that were used for observations and get a better visual sense of what's going on, or if there's anything that's been observed that's close by. But it's really not that efficient for checking a whole list of targets. So what we're going to do is we're going to do that here, and this may be something more like what you would actually do when you're preparing your cycle 3 programs. What we're going to do is define a target table, and all this is an ASCII comma-separated list. And this can come from a string variable in Python, such as this is, where you've got, in my case, I've got a target name, RA-DEC, the range over which I want to search, and a little description. All you really need is the target name and the coordinates. All the other columns are optional, and you can have as many other columns as you'd like. The important thing is that this first line is the header, right, to tell the program what you've got. And the following lines are a comma-separated thing. Every field has to be filled in. Now, the neat thing about that is that when we read the table, this read can actually read that variable, the target table variable. Or if you just give it a file name on your disk, and a CSV file name on your disk, you can read it with exactly the same argument. Only target table is replaced with the name of the file in quotes. Anyway, so let's do that. All right. So what we've got, what I often do is find coordinates in hexadecimal format rather than degrees. But what the following routines are going to need are arguments in degrees. So let's add more columns to the table. All this is doing is saying, well, we've got targets in a table. The same table, we're going to add new columns. They're RA underscore degree, DEC underscore degree, and so on. And this last column here is just a placeholder. It's set to 0. Basically, what it's going to do is count, or be a counter for us to hold account of the matched observations. So here we've made the table, and you can, take a look at it to your heart's content. But you see it's got every one of the targets that we listed. Now this is an optional bit. You can do it if you want to. It's maybe a best practice. But what we're going to do first is, instead of query criteria, which I showed you before, we're going to do query criteria count. And that will just give us a sense of whether there are a lot of observations that match. And if there were like thousands of them, then you might want to worry about whether you want to take some different approach for evaluating what you got back. But here we've got a modest number. There's a few, and quite a lot. But for one target, the center of M31, there are no JWST observations at all within the range that we defined. So you're done. You don't have to worry about M31 anymore in that case. And so we go on to the next set. What we're going to do is examine each one of these rows for each target, and we're going to examine them in somewhat more detail. So we're going to jump through them and apply this query criteria method to get the details, not just the count, but the details. And here's TRAPPIST-1. TRAPPIST-1, recall, had 2 matches in mirror imaging mode. The exposure times are quite long, actually, and I think if you go to this program, you'll find that it was a time series observation. So you're looking at some planet, probably the first planet of, I think there are something like 7 known planets around TRAPPIST, the host star. So that's a program on the title, which may or may not be helpful. And here's the actual program. You can click on that link to the URL for the host. Again, they're probably looking at 1 planet, and there are 6 others to choose from, so that might not be a duplication for you. The variable star XXCHA similarly has observations. Mirror IFU, mirror image, near spec IFU. So it's been observed spectrally fairly thoroughly. And so you'd have to take a look at the program and decide, well, is this really something I want to take a look at or not? If you wanted to do coronography, since it's got a debris disk, it might be interesting to do that kind of observation. And I don't see any coronographic observations here, so that's a possibility. Now M57, which has got a lot of observations. It's the Ring Nebula, and it's also featured behind my head here in the virtual background. And you see we've got MIRI imaging in almost every filter imaginable, near-cam imaging, MIRI IFU, and so on and so forth. Lots of observations. So this one would be tough, right? If you're really interested in this target, you would need to either select a different position within the nebula to do spectra and justify that, or maybe take a look at the central star in time series mode. Maybe that's interesting, who knows? But by and large, now, as for some advice, I mean, it's not all that bad for the TAC to look and say, oh, well, you're going to take advantage of archive data and also do something else new. Maybe that's interesting. But what they would not respond well to is duplication without a pretty good reason. All right, so that takes us to the end of this section, and it's basically a matter of doing all the techniques we covered before, but doing it in a list, which can be pretty efficient. I just want to draw your attention again to this searching by target name or object name. The object name, MAST uses an astrophysical name resolver, either NED or SIMBAD, to look up source coordinates. And not all object names are recognized, for one thing. And different resolvers sometimes return substantially different coordinates. What will happen is MAST will pick one of them, but not tell you which one. So you have to be really careful. Here's a classic example of a bright star mu Arri in the Bayer Greek letter system, and the star MU, variable star MU Arri in the general catalog of variable stars. So if you search for star mu.eri, or displaying mu space ERI, you'll get mu Arri, the Greek letter thing, in one case. For searching for the variable star V star space mu space ERI matches the variable star. Notice the coordinates are quite different. So with a little syntactic sugar, you could be looking for something that's not what you intend. So just be careful. For the target name field, this matches the target names that the investigators used in their observing proposals to refer to sources. And so they're not guaranteed to match standard names for targets, and often don't. And there is no checking of this. We don't go in and correct things in proposals. So you may search for a target name that you think is familiar, find no matches, and be fooled into thinking there's no duplication. So, like I say, it's not recommended. Really, you should use coordinates and coordinate ranges to be perfectly safe.